Hello everyone, my name is Devin Phillips. I am an architect with Red Hat's Cloud Native Runtimes practice, and I'm here today to teach you about how Vert.x is an excellent toolkit for developing applications on Kubernetes. Today we'll talk about a number of different features that make Vert.x a perfect fit for developing applications that can take full advantage of all the niceties that Kubernetes gives us in application development. With that, let's jump right into actual coding. Let's start off by creating a brand new Vert.x project using a Maven plugin. So I'm going to create a directory J4K demo. And then I'm going to do maven io.reactiverse Vert.x maven plugin setup. And we're going to use the latest beta 2 release of Vert.x 4.0. 4.0 should be out anytime now, sometime this fall of 2020. And there we go. If we do a find on that directory, we'll see that we've got a main vertical, we've got our POM file. If we look at that POM file, it is set up to use a parent POM or a dependency management POM that defines the entire Vert.x stack, and then we can just use individual modules from Vert.x. It also sets up the Vert.x Maven plugin, which allows us to do auto redeploys on save, and that allows us to have like a full-blown dev mode. So at this point we can launch this in our IDE. And this is the main vertical that it gives us. And this is our POM with that Vert.x Maven plugin down here that I was telling you about. And we'll begin here by modifying the start method to take a promise of type void. And when you use this method in a vertical, it allows you, when you've done all your setup, when you've gotten this thing ready to do whatever work it is you want this vertical to do, the promise can be resolved either successfully or unsuccessfully to let Vert.x know that you're ready for this vertical to be running and that it's fully deployed. So for example, let's say we need to get our configuration. We need to set up a router. We need to initialize our session management for the web application. We need to add REST endpoints. Actually, we also need to log all REST requests. Set up our event bus bridge, and I'll explain what that means in a little while. And finally, we need to create an HTTP server and attach router to server. And once all of those things are done, then we would successfully resolve that start promise. And if any of it fails along the way, we would just call start promise.fail, and we could pass it an exception or an error message, whichever we should choose. So these are all the things that we're going to do in this demo. In particular, on the config, we're going to get our configuration from a file config and or a Kubernetes config map. We're going to use routing context chaining. And we're going to use socks.js WebSocket for our event bus bridge. And let's get ready to go into the next stage. Now that we have a better understanding of the overall application, we're going to start by implementing the configuration loading code. So the first thing we're going to do is Vert.x file system exists and check to see if there is a config.json file. Regardless of if there is a config.json file or not, we're going to call on success this init config. So on success will be called as long as this returns a result, either true or false. And so it's going to pass a Boolean to this init config method. So we get this method, this init config method, and it gets passed this hasConfig JSON Boolean as a result of this file system operation. Now we're going to use the Vert.x config library, explicitly the Vert.x config Kubernetes config map option. This will also bring in the higher level Vert.x config library. And we're going to create an instance of config retriever options. And what we'll do is we will say if let's say if has config JSON config ops dot add store, and we're going to create a new config store options dot set type is going to be file. Set config is new JSON object. That JSON object puts a path dot slash config dot JSON, and we set format is JSON. So if the config.json file exists, we're going to create a new store. Now, if we've set the environment variable Kubernetes namespace, then we'll assume that we're running inside of Kubernetes, and we're going to say config options add store new config store options. And we're going to say set type config map, set config new JSON object, put namespace, Kubernetes namespace that we pulled out of the environment variable, put name J4K demo. That's the name of the config map object inside the Kubernetes API that we want to retrieve. So we've added these two config stores potentially. We may have added 0 config stores because we might not be running in Kubernetes and there might not be a JSON config file. Or we've potentially added one or both. At which point we can now say config retriever dot create Vert.x with our config options, and we will say listen for changes in our configuration sources, and if there is a configuration change, load our new config. And the load new config method accepts a config change object, and we say this dot current config dot merge in change dot new configuration. So we need to define this current config. Let's go up here and we'll say private JSON object current config equals config. So we'll initialize it with whatever config was loaded on startup. That may be empty. And then anytime we get either a change in this configuration JSON file or a change in this config map, Vert.x will automatically merge those changes into our current config. Newest change wins. So if you start off with name equals my app and the config JSON sets a value of my app or name to J4K, that'll get changed, but then subsequently the config map gets changed to demo, that'll overwrite the change. So newest change wins. Off camera, I went ahead and configured logging through SLF4j. We'll discuss that a little bit more in detail later, but didn't really want to tie up time with that. So let's go ahead and start implementing our router. The first thing we do to implement a router is say router equals router.router, and we pass in an instance of the Vert.x object. Now, anytime we extend abstract vertical, we automatically get this Vert.x object, we automatically get this config method. These are all built into the parent abstract vertical class. And if we want to log all REST requests, we can say router.route handler this log request. And we then implement the log request method, private void log request, and that takes a routing context object. Routing context, you can sort of equate this to an HTTP servlet request. You can access the request, the response, metadata, headers, things like that through the context. But it also does some special things that are specific to Vert.x. So let's say we do log.info, we get a request, and that request has context request path. So we log that path. Now, we still might want to do other processing on this request. So what we can do is we can chain this by saying context.next. So we just implemented a request filter if you think in terms of Spring or JAX-RS or Java EE, we just implemented a filter in 4 lines of code, and that includes the boilerplate. All right. So, in fact, we're showing here our route context chaining. So now we need some session management. All right. Let's do this in a very cool Vert.x way. At a very low level, Vert.x supports clustering. And so if we go in here to our POM and we add Vert.x Infinispan, which is one of several cluster managers that are available to us in the Vert.x ecosystem, we can now, if we set up our application to start clustered, we can use clustered resources. So in a Vert.x cluster, multiple Vert.x instances, whether they're on the same machine or separate machines, can all communicate using the cluster manager and a clustered event bus. And in that clustered event bus, that session management that we're getting ready to create is shared across every node. So if you're using a naive round-robin load balancer, every request coming in that's using session state is going to be shared across every Vert.x instance, every Vert.x node in your cluster. So we definitely want to take advantage of that. That way we don't have to worry about managing session state across multiple nodes. And the way we can implement that is we can say session store clustered session equals new clustered, actually it's clustered session store dot create Vert.x. And then we can say router route handler new session, actually it's session handler dot create clustered session. Excellent. Something else you might notice is that I've been using route with no parameters. This means it takes every path, every HTTP verb. So when we get ready to start adding actual REST endpoints, we could say things like router get API v1 pod info. So let's add an endpoint for our health check. Router get API v1 health z. All right, and again, each of these methods is going to take a routing context object, the same as this log request. And we could call context.next to chain those routes, but probably not in the case of these API endpoints. Continuing on, let's go ahead and implement this getPodInfo method. You can see that I've already stubbed this out. We've got our routing context. And we're going to make use of our clustered session store. So let's start off by saying we want to retrieve our current session. And you see that our routing context has the session information associated with it. Let's create a new JSON object that's going to have our response for our pod info. And in that pod info, let's put our unique ID. And you'll see that up here I added an instance ID. This is Initialize as soon as the application is started. It's just a random UUID so that we can identify each pod separately. Now, let's create an integer called request count. And let's use our session data get or default So what we're saying is inside of our session, inside of the data contained in that session, we're going to get the request counter or we're going to default to 0. And we're going to do session data put request counter request count plus 1. So we're going to increment our request counter inside this shared session. And we're going to put the request counter into our podinfo JSON. And then finally, we're going to send a response. The response is going to be context.response.set status code 200 set status message. Okay. Put header content type application JSON and end with our pod info encode prettily. We can also log our pod info response with that same pod info encode prettily. There we go. Earlier I mentioned that when we're doing a clustered Vert.x application, part of that cluster is the event bus. In Vert.x, the event bus is how you can coordinate work across multiple threads, verticals, nodes, instances, whatever, in a way that's non-blocking and doesn't require shared memory. You just send a message through the Vert.x event bus. Every node that's a member of the cluster forms a mesh network with their event bus so that they can send and receive messages back and forth. So we would also like to be able to extend that message bus out to our user interface, perhaps over WebSockets. And Vert.x has a way to do that using the Vert.x event bus bridge capability. Now there are multiple different types of event bus bridges. Today we're going to talk about the WebSocket event bus bridge. In order to implement the WebSocket event bus bridge, the way we're going to do that is we're going to add a sub router to our router. And so we're going to say router.mount subrouter. And we're going to say the mount point at which we're going to mount that subrouter is going to be API event bus. So any request that starts with API event bus is going to get delegated to this subrouter. And in that subrouter, we're going to create our event bus bridge using WebSockets. And in this case, I'm actually going to create a method sock.js event bus bridge so that I can keep this configuration separate, keep things a little more readable inside of the main method or the start method. And private router create sock.js event bus bridge, takes no parameters. We're going to say final sock.js bridge options. Yep. Sock.js event bus bridges work over WebSockets, which means we're extending functionality across the event bus to the web browser. So we want to be careful about what exactly we expose. We don't want to give just everything access over the event bus. So what we can do is we can say .add inbound permitted and a new permitted options. Set address regex, and so we could set a regular expression to say which event bus addresses we're going to allow access to. Now we don't have anything to be worried about in this application. We're not really creating anything else on the event bus that we would be concerned about. So I'm just going to put .star. That's going to allow everything. And then we want to also do the similar configuration for the outbound message bus. So we've got our Sock.js bridge options. We can now return a Sock.js handler, which we create with the Vert.x instance, and we bridge with our bridge options. And so this bridge method returns a type router, which we mount as a subrouter. This uses the Sock.js event bus bridge to extend messaging to and from for the browser, which I'll show you how we use that later. Up to now, we've mostly been configuring our router. We haven't actually set up an HTTP server to handle those routes. I want to show you how quick and easy you can accomplish that in Vert.x. It's Vert.x, create HTTP server, and if you want, you could pass different options, and this is how you would configure things like SSL or Alpine support or HTTP 1.1 or 2.0 support, things like that. The default HTTP server works really quite well, especially in Kubernetes. And we tell it to handle requests using our router, and then we tell it to listen on a given port. And in this case, it's going to be current config, get integer, port, and if that's not set in the current config, we'll default to port 8080. We'll get our server object, and we can say start promise complete. And we can say on failure, start promise fail with the error that caused it. And thus, we have created our HTTP server and attached our router to the server. Started listening on whatever configured port or port 8080 by default, and if successful, we complete the future to tell Vert.x, hey, we've successfully started this main vertical. This main vertical is completely up and running. Otherwise, on failure, we'll tell Vert.x the main vertical didn't start properly, and in fact, Vert.x will probably exit at that point. Let's now use the shared data structures that are available to us in the Vert.x cluster manager. And to get started with that, we're going to take advantage of another feature of Vert.x called Composable Futures. This listen method is an asynchronous call that returns a future that will resolve when an HTTP server is either successfully created or has an error. For example, maybe the port's in use or something. Which means that this future will resolve either with an HTTP server reference or with an exception. And we can compose that with another asynchronous method. So let's say this init shared data counter compose this store counter reference. And then we can implement those two methods such that store counter reference returns a future of type void, which means that we no longer need to make these signatures match up this way. We can just use a method reference. And then IntelliJ will actually help us create this method by stubbing it out. It's going to be a future of type counter. And it's going to accept an HTTP server. We're not actually going to use that HTTP server because we just want to make sure that it's there. So we can say return Vert.x shared data get counter. And we're going to call this counter message counter. And we'll create a constant, and that constant will be message counter. There, that piece is done once we put a semicolon on. So you'll see that this now has turned white. It's all good. We can implement this next method. And this method is going to return a future of type void. It's going to accept our counter instance. And we're going to say this dot counter equals counter. I'm going to say alt enter, create that field of type counter. And now both of these methods match up, and you see that this all turns white, meaning that all the method signatures are appropriate. So now we have a reference to this shared data counter that we can use in our next step. Using the shared data counter, we want to set up to be able to use that clustered event bus to send messages across all instances of the cluster. And in order to accomplish that, we're again going to compose a new method, this setup periodic event bus message. And we can create that method, and it's going to return a future of type void. It's going to accept a void, and it's going to return a future succeeded future. Now, succeeded future without any parameters returns a future of type void. So what we're going to do is we're going to use Vert.x's capability to do a timer or set periodic. So there is Vert.x set timer, which after a delay will run a method once, and there's Vert.x.set periodic, which will run a method every n number of milliseconds. In this case, we're going to set periodic every 500 milliseconds. We're going to send a message. This send trigger message send, and we can create that method. And the value that gets sent into that method is the timer ID, so that at a later point, if you wanted to, you could say Vert.x.cancel-timer and put in that timer ID. We're not actually going to use that in this demo application. Just want you to be aware of that. Counter dot increment and get dot on success this send status message, on failure log that error. Now, most methods in Vert.x are fluent, meaning that we can chain things together and still get a good result. So for example, these composes that we chain together in a Fluent API. So now we implement that send status message. And in this case, it's the count that we're getting. And we just create a new JSON object. And we're going to use that Fluent API to put the ID of the node, our instance ID. We're going to put constant for that. And that's going to be current config get string app name. With a default of J4K. And finally, we're going to put message count into that message. And we're going to ask Vertex to use its event bus to send a message to an arbitrary address of status. Now, event bus addresses can be any arbitrary string. Just want to be careful that you make your strings unique throughout your application. So in general, it's a good practice to use reverse dotted FQDN notation. So if I were really going to be writing an application, I might use com.redhat.j4k.vertex.status as my event bus address so that it's identifiable and unique. But today, for this demo, we're just going to put status and message. Now, because JSON object has a method on it that allows it to be serialized to a byte buffer, a buffer object in Vert.x, I don't need to do anything special, but I could, for any type that can be converted to a string or that is a string, it can be sent on the event bus. Otherwise, that class type has to implement a serializable interface like Jackson annotations or using some sort of toString, or it needs to be annotated as a data type in Vert.x, which means that it will need a toJSON method. The very last thing we're going to do inside of our application is set it up to serve some static HTML, JavaScript, and CSS resources so that we can have a user interface. I have already pre-made a user interface in Vue.js, which can connect to our WebSocket event bus bridge. And to do that, we're just going to say router.get without any sort of path. So it's anything that isn't previously handled in the router is going to fall through to this get method. And this get method is going to have a static HTML handler. So we're going to say this dot config static handler. And that method is going to return a handler of routing context. In fact, it's going to return a static handler, which implements that signature. And we're going to say return static handler dot create. I'm going to use that Fluent API again. Set index page to be index.html dot set caching enabled true, because we don't expect that content to change. Set files read only, because we don't want people to be able to upload. And set directory listing false, because we don't want people to list our directories. And there we have it. Our router will now serve static content. By default, it will serve it from within the class path from a web root directory. We can override that here. We could say dot set web root, And we could make this an arbitrary path that we could configure, in fact. So we could say current config get web root, and the default would be web root. Let's actually get string. So let's go ahead and do that just for clarity's sake. Let's see what this all looks like when we put it together into a fully running application on a Kubernetes cluster. You'll see that I've fired up Minikube. I'm using Minikube for simplicity, but you could also use code-ready containers. You could also use kind. And to simplify this, I've actually created a Helm chart to deploy the application. This will be available in the repository that I'll link you to at the end. And it's in the J4K demo Kube Vert.x demo. And we can just say Helm, by the way, I'm using Helm 3, install J4K demo / set use router or use route equal false. So this Helm chart is compatible with both OpenShift and regular Kubernetes. And on OpenShift, you would generally use a route object for your ingress. In stock Kubernetes, you would use an ingress object. So if you're using this on anything other than OpenShift, you need to set use route equal false. Otherwise, you need to set use route equal true. Boom. Now it's deployed. Let's launch the Minikube dashboard. And you'll see that our application is deploying. I've pre-published these container images to Docker Hub, so you can deploy this as well. So if we look at our deployments, we see our J4K. It was created 53 seconds ago. We could go in here and we could see all of the pods that make up the current deployment. Currently there's only one pod. We could tail the logs, and we see that the health checks are polling the root, and our log all requests is logging those requests. If we go down here to ingresses, our ingress is now up. If we click on the ingress, we see our nice Vue.js application UI, and you'll see in this that we have a pod. The number in parentheses is the REST request count that's getting stored in our shared session. If you recall, our shared session is clustered across the Vert.x cluster. Shows our default application name, which is being defined in our default configuration. Shows our pod unique ID. And this timestamp you see down here, every time it updates, that's because of messages on the event bus. So right now we only have one pod, so we're only getting messages from one pod in the event bus. Let's actually scale this up. So if we go to our deployments, we go here and we scale to 4 pods. After a few moments, before the health check is even ready, you'll start to see pods populate into this list because we're getting messages from more than one pod now. And each pod has their own unique timestamp instances. And every 10 seconds, you'll see the screen refresh reload. It's because we're trying to break our connection and form a new connection. And you'll see that that colored block changes to a different node. It's because our ingress is set up to not do session affinity. So every time we reconnect, we connect to a different pod. And the event bus is connected, our WebSocket event bus bridge is connected to that pod. And our REST request is coming through that pod. And as such, that means that if there were differences across the pod, we should see across the various pods, we should see them, but we don't see any differences because the cluster is working effectively. But let's take a look at what happens if, for example, we kill a pod. Let's just delete a random pod, and we'll see that the time stop incrementing on this one. This must be the one I killed. And after a few seconds, my application will notice that it will spawn a new pod, and the old pod will disappear. Kubernetes automatically recovered. And the new pod automatically picked up where the old pod left off. It had the same shared session state. It had the same shared counter. It's sharing the same exact event bus. This, I think, alone makes Vert.x one of the premier development toolkits for running in Kubernetes or the cloud. Now, we also have a config that is Kubernetes based. Right now, if we look, we don't have any config maps defined, but if you recall, our application is set up to watch for config map changes of a particular type. So if we switch back over here, you'll see that I have a config map YAML here, pre-made. And if we do kubectl apply -f config map, and we switch back over to our application, here in a few moments, you noticed our application name changed. That's because the config map changed the app name value. And our application, without ever restarting, without ever having to reload, just automatically got that configuration update. And we could do that multiple times. So if I were to edit the config map and say Vert.x rocks and apply that config map, boom, after a few seconds you see that all of the nodes update. They get their Kubernetes config map updates asynchronously from the Kube API because it's constantly watching for those config map changes. That concludes the demo, and I want to thank you for taking time to sit with me today and learn more about Vert.x and how you can effectively leverage many of the capabilities in Vert.x inside of a Kubernetes environment. And please feel free to check out the Git repository that I'm going to link you to at the end. It will have the full source code, the Helm chart, the config maps, all of this information that you need, along with a very complete lab guide of how you can accomplish this exact same application or a similar application yourself. Enjoy the rest of the conference. It's been a privilege to be invited here to join you and talk at J4K. And please make sure you check out our sponsors who have made all of this possible, one of which is my employer, Red Hat, full disclosure. And it's been a fantastic experience. Thank you.